All right, I use my strong words. Thank you very much. It's a pleasure to be here and to recognize Shukla's undetermined birthday, but we know approximately what it may be. What I would like to talk about shortly here, instead of just picking out one particular area and go into detail, I will make a relatively broad spectrum of a few issues which Shukla and I have been discussing actively over the years. And in fact, I will say a little about what progress we have made in numerical weather prediction and what it means for climate simulation studies, and also really discuss some of the different ways where we sensibly can use climate or weather forecasting models in combination with observations. I am a little, having been working with forecast practically all my active life, I am naturally a bit skeptic about things because forecast has to be validated. And if you have users of forecast, they tell you if they disagree with reality. And therefore, I think that creates a certain attitude. But anyhow, you have seen all this. I was very happy at ECMWF when I could convince Ed Lorenz to spend a sabbatical at the center. And he did this very interesting study, which most of you have seen, that is actually a way to estimate predictability of weather predictions, or predictability of the first kind, as Lorenz called it, by simply investigating, comparing the forecast with the growth rate of forecast, which we can call the lower bound, which is here the upper curve, and the upper bound, which is then essentially the difference between consecutive pairs of forecast, which you could see as a way of perturbation in a realistic way. And one of my co-workers in Reading, Lizzie Frode, actually repeated this work by comparing the result from 1985 and 86, which was a little better than it was in 1982, hopefully. I was director then, so of course I have to use the best of the situation, with the result some 15 years later, which is a red curve. And what you can see here is that the forecast has definitely improved, partly because of initial error, but also the predictability estimate has changed. But at the same time, you can notice that the difference between the lower and upper bound is now much closer together. And this is actually confirmed, more or less, by what has been achieved in practice, namely that the forecast skill has certainly improved considerably over the years, with actually so much that the European Centre actually have been living up to its promise, namely to make a 6-day forecast, which was as good as a 2-day forecast when the centre was planned. Actually, this is much better. Actually, now a forecast for more than 9 days is actually as good as his early forecast in the 1970s and before. Now, there is, of course, an interesting approach to predictability, and I asked Lizzie Frode, why not take a look on the ensemble mean forecast and do the same thing as Lorenz did with the actual forecast. And what you can see here, that you have a quite different behavior, that the estimate of predictive skill here is actually significantly smaller than the actual skill, and is actually slightly reducing with time. Now, this can, of course, be misunderstood. In some way, you can say the ensemble forecast is improving, but the value of the forecast is actually at the same time falling down. And you can think that you make an infinite number of members, and you calculate the ensemble for an infinite long time, then in fact what you will produce, if you have a good model, is just the climate variability. So you get information about climate, but of course the usefulness of it is of course not as high. And you can get an idea from this by looking upon this example here of 3 forecasts, one for 14 days, one for 14.5 days, one for 15 days, both for the actual prediction, which happened to be an actually good forecast on the top, and below there you have the same ensemble forecast for the same period, and on the side you have actually the analysis, which is a verification. So this is actually forecasts which are made up to this very day. And what you can see there is that the actual forecast contains much more features than the, as you can combine analysis, but the ensemble forecast is more smoothed out, but on the same time it's more robust. So it's not that easy to determine the actual value of it. You have some confidence in the ensemble forecast, but at the same time the information is falling, as you can see. Now, the way to use predictions in ensemble mode is simply to make use of all the individual members. And this is actually the storm tracks of the Hurricane Sandy. They have been indicated here in different colors. The lifetime of Sandy was something like 3 weeks, starting somewhere in the Central Atlantic, moving into the Mexican Gulf, and then moving northwards. And you can see there that if you take the forecast about 12 days before, when the storm was south of Cuba, then in fact practically all the forecasts put it out into the Atlantic, which is the most common thing which is happening. But anyhow, when you come closer to the end of the storm, sort of 6-7 days before, then in fact the forecast, both from ECMWF and from NOAA, is actually quite accurate. The European Center's forecast happened in this case to be a little more accurate because it could find the most realistic paths a few days before. But that is just an example that you use the whole information content in an ensemble run, and not only the mean or any individual forecast. So that is, I think, the way the service are using it. And in fact, we probably have to use the techniques even in climate models. Now, there is no question that among the greatest success we have had has been in extratropical storms, which are surprisingly well simulated. This is actually a presentation which was done by Kevin Hodges, and it shows the generation or the genesis of extratropical storms, that is on the top, and to the left side, that is actually from era 40 interim, and on the other side is from ECAM 5, climate integration. And it's very hard to see any difference between areas. You probably get all the different spots where you have cyclonic developments, which just gives an indication of the strengths today of the general circulation models. And on the lower part, you have the density tracks of the storms. And you can see, for example, the generation of storms on the lee side of the Rocky Mountains, second one on the east coast here in the United States, and of course of the very marked center in the Mediterranean. This is, of course, during the winter season. And the storm tracks, of course, you can follow, for example, here in the Mediterranean. So that is, I think, is a great success. And if we look upon the individual storms which can be extracted, and this shows essentially the development of the 100 most powerful storms. So this is an ensemble of cyclones which has been extracted from the run. This is a 50-year integration with a relatively high resolution model, T200 something. And it shows the maximum time of the maximum deepening, which is the wind speed and the precipitation, the time of maximum precipitation, and the time on the bottom, which is the maximum intensity of the storm. And I will not show you the result from the era 40, but that looks practically the same. I will instead show you these things which probably you are not so used to see. That is actually the occlusion of these ensemble cyclones. And there is a line for each 6 hours. And you can see on the top, that is the ECAM 5, below you have the era 40. You can see the speed of the occlusion process, which is actually very well predicted or simulated by the system, and after something like not more than about 18 hours, we go from a full intensity to essentially a state where there is no tilt of the storm. So that is, I think, just an example of what has been achieved by general circulation models, which I think is not unusual. You probably have that in most models today. Now, and this is something which is just an example. It's a little difficult to calculate, but this is essentially the momentum Lagrangian transport of kinetic energy out of the storms. And you can see this at the time of the maximum development, peak intensity, and it demonstrates the very rapid generation of energy from the occluding storm into the large-scale circulation. So this is, of course, where the storms are maintaining the semi-permanent systems of circulation. And I think this is also something quite impressive. Now, an area which Shukla and I have been discussing over the years, of course, is reanalysis. And in fact, we started that already in the 1977 at ECMWF, where we did 1 year of simulation by the figure data. Of course, that was a very hard time, but I had it as a backup system for the center's operation if the operation department would have failed. So that actually was a very good strategic thing. They actually managed, so we had no problem, but we had that as a backup system. But that was essentially a learning exercise, and then after that, the European Center and many others have continued this work. And this is just a very recent calculation which we did, where we wanted to investigate how can we really use now the reanalysis to identify climate change or a trend. And I think if you look over the land areas on the top, that is the surface temperature, 2-meter temperature, comparing the European Center reanalysis with both GISS and Hadley Center, they are practically identical. And they show something like a 1/4 of a degree per decade. So actually there is a much more rapid warming of a continent than it is of the ocean, as you can see on the second line, where the European Center probably somewhat underestimate the warming because of some difficulties I had with the ocean surface temperature, the southern hemisphere. Yes. And then I think the lower one, that is actually the corresponding calculation of the actually temperature trend in the free atmosphere. And in fact, what I have suggested recently is that we should probably use the temperature of the troposphere in climate sensitivity studies instead of using the surface temperature, because that is much more robust. As you can see here, simply the typical temperature trend in a map form. So it's sort of, there is no clear structure there between oceans and land. It's simply more or less the same. Now, one important way to really use climate models is to try to use them to detect climate signals. And this is actually, map shows the change in the Nygårdsbreen, which is a glacier in Norway, and how it has varied in the observational case here over something like 350 years. And the curve here is actually a simulation studies by a coupled system where a glacier model is become to a region model to downscaling to a DCM, and that has generated a stochastic variability of the position of the glacier. And if you then simply make a statistical comparison of that, then you can then, the result is that the probability that the change up to from the Little Ice Age to 1900, that is actually has a very small, relatively high probability, so it's 74% that this can happen by chance every 2,000 years. But if you take it up to our present time, then in fact the probability actually drops down to something like 3.8% that this can happen once in 2,000 years. So that is a sort of an indication that this is very unlikely that this retreat in the recent 50 years or so can happen just by chance. This is, of course, related to the structure of the model, but this is just a technique which is very useful, which we can apply on all sorts of areas. And finally, I will just show you a validation of Lorenz's idea of predictability of the second kind, and that is to validate the statistics of a model. And this is a model which has been integrated over 500 years, and we have used observation data for Europe put together by Lutherbacher, and then what you see here on this figure is actually an ensemble of the 10 coldest winters in Europe simulated by the model and as observed by these Lutherbacher's data. And below there you can see the typical global anomaly for the model simulation because we don't have the observations. And that indicates there is a typical pattern of these kind of extreme events, which you can also find similar for the United States, which are actually a part of the natural behavior of the climate system. So it doesn't have to be in no way related to any external forcing. That is something what the climate system can do on its own. And this is something we need to know in the same way. And then finally, this is my last figure. This is maybe difficult to see, but that is just simply an indication of how surprisingly good the model is to reproduce not only the mean and the standard deviation, but also the maximum and minimum of the warmest and the coldest winters over more than 200 years of data. And I could just show here something from Paris, for example, and the little figure here on the side, that is actually the observed data. And here you have actually similar model. And there is actually surprisingly good agreement. Where there is a difference, this is due to local conditions, like, for example, close to the shores of the ocean, because this is not actually a statistical downscaling. This is simply just the output from the model itself. So that is, I would say, show this as an example of that we actually can validate predictability of the second kind, and that is something which I encourage you to do, because it could be another further way of getting confidence in general circulation model, because we cannot get confidence in forecast which we haven't validated yet, and this is of course a problem we have with the climate simulations. And then finally, congratulations Shukla and warm thanks for our very stimulating cooperation. I put up here for more than a quarter of a century. I don't know exactly when it started, but probably it is of that order of magnitude at least. Thank you. Questions? Deep Lennart,
can I just provoke you to be... I kind of gave you the impression at the beginning of your talk, I had the impression at the beginning of your talk that you expressed a little bit of skepticism, let's say, about climate models. And yet, well, hang on, and yet all of your...
About climate simulation.
Okay, but all of your, the results you presented suggest the models are actually doing a pretty good job. So I just wondered what it is you feel uncomfortable.
We just have to use them in the right way.
And what does that mean exactly?
Well, we shouldn't make focus, we should make scientific evaluation of them, as I have demonstrated in these cases.
Okay, and Lennart, the echo model was coupled to it, right?
Yes, of course.
Lennart, both Jim Palmer and I had a long debates with the IPCC leaders of modeling. In one IMS meeting, I remember Tim and I standing at one spot for 90 minutes. And the claim was, and I want to mention names, but just sort of one of the modeling groups that, look, just because your model is good in predicting El Nino or seasonal forecasts or changes, doesn't mean I believe your model's prediction of the global warming. Do you remember that, Tim? Yeah, that has been sort of, yeah. And
No.
we don't agree with that. We agree with you, but can you imagine?
Yeah, I think the main thing I wanted to highlight was that we need, of course, to understand what are internal properties of the climate system, which we can call chaotic if we want. We can relate it to certain type of processes. But I mean, if you say that if you have high precipitation in Norway when you have a warm phase of the North Atlantic Oscillation, this is of course trivial because you then have to predict that right phase of the North Atlantic Oscillation. So I think one has really to recognize that you have some users of these forecasts, and if the users are not happy with the forecast because they don't agree with reality, then we have a problem. And my criticism perhaps to climate simulations over 100 years is that if people take it for what they are of course important. They are used for risk assessment, and that is perfectly correct. But I mean, to consider them as a sort of a predictions for the future, that is a complete mistake, because we cannot say anything about that.